Good day, everyone. Welcome to my session on Teaching Beyond the Box entitled Critical Content in Mathematics. What I am going to share is about solving logarithmic equations and inequalities in general mathematics, which is one of the core subjects in the senior high school. In this session, we will have first a review of the important concepts in logarithm to refresh our minds before we proceed with solving. At the end of the session, participants will be able to revisit the definition of logarithm, transform exponential form to logarithmic form and vice versa, recall the laws and properties of logarithm, determine the properties of logarithmic equation and inequality, and lastly, solve logarithmic equations and logarithmic inequalities. To start this session, let's have first a better or say deeper understanding about logarithm. Now, what is logarithm? This will answer the question, how many of x number do we multiply to get another number? You may say, oh, that is an exponent. Yes, you are correct. At the same time, the question is asking you to get the logarithm. Let's have an example. How many trees do we need to multiply to get 81? As shown, the answer is 4. So again, what do logarithm tell us? It tells us what the exponent is. Remember that logarithmic function is the inverse of exponential function. Let's discuss these three important numbers in logarithm. The base, the number that we are multiplying. The logarithm, how often we multiply the number. And the argument, the number we want to get. Let's take 3 raised to 4 equals 81 as an example. This is written in exponential form. We have the base 3, the exponent 4, and the number that we want to get is 81. Let us transform this to its equivalent logarithmic form. The logarithm of 81 base 3 equals 4. Where the base is 3, the argument is 81, and the logarithm, that is 4. Let's practice. Transform the following exponential form to logarithmic form. Number 1. The cube of 2 equals 8. Number 2. The cube of 1/2 equals 1/8. Number 3. 4 square equals 16. Number 4. The cube of 2/3 equals 8 over 27. Let us check. For number 1, the equivalent logarithmic form is the logarithm of 8 base 2 equals 3. For number 2, the logarithm of 1 over 8 base 1/2 equals 3. For number 3, the logarithm of 16 base 4 equals 2. And lastly, number 4, the logarithm of 8 over 27 base 2/3 equals 3. Here is the formal definition of logarithm. Let a and b be positive real numbers such that b is not equal to 1. The logarithm of a with base b, denoted by log a base b, is defined as the number such that b raised to log a base b equals a. That is, logarithm of a base b is the exponent that b must be raised to produce a. Here are some important terms in logarithm. Common logarithms are logarithms in base 10. A logarithm written without a base means that the base is 10. For example, logarithm of x base 10 or log x. We have also the natural logarithms. These are logarithms using Euler's number as its base. The Euler's number is approximately 2.718281828. For example, the logarithm of x base e or ln x. Be careful when to use the logarithm of x base 10 or log x and logarithm of x base e or ln x, because sometimes learners usually mistakenly think that log x is ln x or log x base 10 is ln x. Let us understand more the nature of logarithms. Can we have a negative logarithm? Yes, since logarithms deals with multiplying, hence negative denotes dividing. For example, the logarithm of 1 over 81 base 3 equals negative 4. Can we have a zero base? The answer is no. When you have a power function with base 0, the result of that power function is always going to be 0. In other words, there is no exponent you can put on 0 that won't give you back a value of 0. Or put it in a different way, 0 raised to anything is still 0. In the same way, 1 raised to anything is always 1. Now, can we have a negative base? If you raise a negative number to a positive number that is not an integer but instead a fraction or a decimal, you might end up with a negative number underneath a square root. For example, negative n raised to 1/2 is equal to the square root of negative n. And as you know, unless we're getting into imaginary numbers, we can't deal with a negative number underneath a square root. So 0, 1 in every negative number presents a potential problem as the base of a power function. And if those numbers can't reliably be the base of a power function, then they also can't reliably be the base of a logarithm. For that reason, we only allow positive numbers other than 1 as the base of the logarithm. Then what we know is that if the base of our power function is positive, it doesn't matter what exponent we put on that base. It could be a positive number, a negative number, or 0. That power function is going to come out as a positive number. To summarize, since we only allow the log's base to be a positive number not equal to 1, that means the argument of the logarithm can only be a positive number, which means that in order to protect our bases, we must only allow positive arguments inside the logarithm. Again, let's take it one by one. The base of logarithm can be only positive numbers not equal to 1. The argument of the logarithm can be only positive numbers because of the restriction on the base. And lastly, the value you get for the logarithm after plugging in the base and argument can be positive or negative numbers. Let us recall the laws of logarithms for x greater than 0 and b not equal to 1. We have logarithm of 1 base b is equal to 0. For common logarithm, we have log 1 equals 0. The logarithm of b base b is equal to 1. For common logarithm, we have log 10 is equal to 1. The logarithm of b raised to m base b is equal to m. For common logarithm, log 10 raised to s equals s. B raised to the logarithm of x base b is equal to x. For common logarithm, we have 10 raised to log x is equal to x. The logarithm of 0 base b is not defined. Also, the logarithm of negative x base b is not defined. We have also the change of base formula. Log x base a is equal to the logarithm of x base b over the logarithm of a base b. Examples. Log 1 base 8 equals 0. Log 4 base 4 equals 1. Log 5 raised to 3 base 5 equals 3. 3 raised to log 6 base 3 equals 6. 2 raised to log 7 base 2 equals 7. Lastly, the logarithm of x base 2 is equal to log x over log 2. Properties of logarithms. The product rule. The logarithm of m times n base b is equal to the logarithm of m base b plus the logarithm of n base b. For example, the logarithm of xy base b is equal to the logarithm of x base b plus the logarithm of y base b. Let us try this. What is the logarithm of 6? Applying the product rule, this is equal to the logarithm of 2 plus the logarithm of 3. Also, what is logarithm of 9b base 3? This can be written as the logarithm of 9 base 3 plus the logarithm of b base 3. Let's have some more practice. Express the logarithm of 42 base 3 as the sum of two logarithms. We can rewrite this as the logarithm of 2 base 3 plus the logarithm of 21 base 3. Also, logarithm of 3 base 3 plus the logarithm of 14 base 3. And logarithm of 6 base 3 plus the logarithm of 7 base 3. Let's have some more. Express the logarithm of 20 base 5 as the sum of two logarithms. We have logarithm of 2 base 5 plus the logarithm of 10 base 5. Also, logarithm of 4 base 5 plus the logarithm of 5 base 5. Take note of this common error. The logarithm of 8 times 4 base 2 is not equal to the logarithm of 8 base 2 times the logarithm of 4 base 2. It should be the logarithm of 8 times 4 base 2 is equal to the logarithm of 8 base 2 plus the logarithm of 4 base 2. The quotient rule. The logarithm of m divided by n base b is equal to the logarithm of m base b minus the logarithm of n base b. For example, the logarithm of x over y base 5 is equal to the logarithm of x base 5 minus the logarithm of y base 5. Let us try this. What is the logarithm of a over 5 base 2? Applying the quotient rule, this is equal to the logarithm of a base 2 minus the logarithm of 5 base 2. Another example. What is the logarithm of mn all over p base 2? Again, applying the quotient rule, we have the logarithm of m base 2 plus the logarithm of n base 2 minus the logarithm of p base 2. Express logarithm of 4 base 3 as the difference of two logarithms. Applying the quotient rule, we have the logarithm of 8 base 3 minus the logarithm of 2 base 3. Also, the logarithm of 12 base 3 minus the logarithm of 3 base 3. Let us try another problem. Express the logarithm of 2 base 5 as the difference of two logarithms. Applying the quotient rule, we have the logarithm of 10 base 5 minus the logarithm of 5 base 5. Also, the logarithm of 20 base 5 minus the logarithm of 10 base 5. Again, beware of this common error. The logarithm of 8 divided by 4 base 2 is not equal to the logarithm of 8 base 2 divided by the logarithm of 4 base 2. It should be the logarithm of 8 divided by 4 base 2 is equal to the logarithm of 8 base 2 minus the logarithm of 4 base 2. The power rule. The logarithm of m raised to x base b is equal to x times the logarithm of m base b. For example, the logarithm of b raised to 2 base 5 is equal to the logarithm of b base 5. Another example, we have the logarithm of 5 raised to x base 2 is equal to x times the logarithm of 5 base 2. Let us try this. What is the logarithm of a raised to 3 times b raised to 4 base 7? This is equal to 3 times the logarithm of a base 7 plus 4 times the logarithm of b base 7. Here are some important concepts to remember. The square of the logarithm of m base b is equal to the logarithm of m base b times the logarithm of m base b. Let us summarize the properties of logarithms. We have the condensed and expanded form. For number 1, we have the logarithm of m times n base a is equal to the logarithm of m base a plus the logarithm of n base a. For number 2, we have the logarithm of m over n base a is equal to the logarithm of m base a minus the logarithm of n base a. And lastly, we have the logarithm of m raised to r base a is equal to r times the logarithm of m base a. These properties are based on rules of exponents, since logs equals exponents. One-to-one property of logarithms. If m equals n, then the logarithm of m base a is equal to the logarithm of n base a. If logarithm of m base a is equal to the logarithm of n base a, then m is equal to n. This one says, if two numbers are equal and you take the log of both sides, then they are still equal. This one says, if you have an equation and each side has a log of the same base, then the arguments of both sides are equal. Using the log properties, write the expression as a single logarithm or in condensed form. The problem is 2 times the logarithm of x base 3 minus 1/2 times the logarithm of y base 3. Solution. Applying the third property of logarithm, which is the power rule, we will have the logarithm of x squared base 3 minus the logarithm of y raised to 1/2 base 3. Then applying the second property of logarithm, which is the quotient rule, we will now have the logarithm of x squared over y raised to 1/2 base 3. Let's have another problem. Using the log properties, write the expression as a sum and or difference of logs, or in expanded form. The problem is the logarithm of ab raised to the 4th power divided by the cube root of c squared base 6. When working with logs, rewrite any radicals as a rational exponent. Hence, this is just equal to the logarithm of ab raised to the 4th power over c raised to 2/3 base 6. Applying the second property of logarithm, which is the quotient rule, we will now have the logarithm of ab raised to the 4th power base 6 minus the logarithm of c raised to 2/3 base 6. Then applying the first property, which is the product rule, we now have the logarithm of a base 6 plus the logarithm of b raised to the 4th base 6 minus the logarithm of c raised to 2/3 base 6. Then, applying the third property, which is the power rule, we will now have the logarithm of a base 6 plus 4 times the logarithm of b base 6 minus 2/3 times the logarithm of c base 6. Properties of logarithmic functions. If b is greater than 1, then y equals the logarithm of a base b is increasing for all a. Now, if the base is greater than 0 but less than 1, then y equals the logarithm of a base b is decreasing for all a. Let's proceed with the strategies to solve logarithmic equation. First, rewriting to exponential form. Second, using logarithmic properties. Third, applying the one-to-one property of logarithmic functions. Then fourth, the zero factor property. That is, if AB equals 0 or B is equal to 0. Let's have example number 1. The logarithm of 2x base 4 equals the logarithm of 10 base 4. Solution: applying the one-to-one property, we have 2x equals 10. Dividing both sides by 2, we have example number 2. The logarithm of 2x minus 1 base 3 equals 2. Solution: transform the logarithm into exponential form. So we have 2x minus 1 equals 3 squared. Simplifying, we have 2x equals 10, divide both sides by 2, therefore we have x equals 5. To check, the logarithm of 2x minus 1 base 3 is equal to the logarithm of 3 squared base 3 by transforming the right side of the equation to the logarithm with base 3, since the left side of the equation is also in base 3. Simplifying and plugging in the value of x in the equation, we have logarithm of 9 base 3 is equal to the logarithm of 9 base 3. Therefore, we can say that 5 is a solution. Example number 3. The logarithm of 16 base x equals 2. Solution: transform the logarithm to exponential form. So we have x squared equals 16. By adding both sides of the equation by negative 16, therefore we have x squared minus 16 equals 0. Factor x squared minus 16. So we have the quantity x plus 4 times the quantity x minus 4 equals 0. Apply the zero product property. Therefore, we get x equals negative 4 and positive 4. As what you can see, in the given problem, x is the base. The base must not be a negative number. Therefore, negative 4 is not part of the solution. Let us try for if it is really a solution. To check, we have the logarithm of 16 base 4 equals 2 times the logarithm of 4 base 4 by changing the right side of the equation to the logarithm with base 4. Simplifying, as observed, the left side and the right side are equal. Hence, we can say that 4 is a solution. Example number 4. The logarithm of the quantity x plus 1 base 2 plus the logarithm of the quantity x minus 1 base 2 equals 3. Solution: applying the product rule of logarithm, we have logarithm of the quantity x plus 1 times the quantity x minus 1 base 2 equals 3. Transforming logarithm to exponential form, so we have the quantity x plus 1 times the quantity x minus 1 equals 2 raised to 3. Simplifying, we have x squared minus 1 equals 8. By adding both sides of the equation by negative 8, so we have x squared minus 9 equals 0. Factor x squared minus 9. So we have the quantity x plus 3 times the quantity x minus 3 equals 0. Now apply zero product property. Therefore, the value of x equals negative 3 and 3. Let us check if negative 3 could be a possible solution in the problem. Possible solution. So by plugging in negative 3 to x in the argument. So negative 3 plus 1 is negative 2. So in this case, the argument is already negative 2. So definitely, negative 8 is not part of the solution. So let us check 3. 3 plus 1 is 4. 3 minus 1 is 2. Therefore, the argument is positive. So let's continue. The logarithm of the quantity x plus 1 base 2 plus the logarithm of the quantity x minus 1 base 2 is equal to 3 times the logarithm of 2 base 2. Here, we transform the right side of the equation to logarithm with base 2. Let's proceed. Plug in the value of x in the equation. So we have now the logarithm of the quantity 3 plus 1 base 2 plus the logarithm of 3 minus 1 base 2 equals the logarithm of 2 cubed base 2. Simplifying, we have logarithm of 4 base 2 plus the logarithm of 2 base 2 equals the logarithm of 2 cubed base 2. Again, we have the logarithm of 4 times 2 base 2 equals the logarithm of 2 raised to 3 base 2. Simplify again. So we have logarithm of 8 base 2 equals the logarithm of 8 base 2. As what you can see, they are equal. Hence, we can say that 3 is a solution. Example number 5. The logarithm of x squared equals 2. Solution. Transform logarithm to exponential form. So we have x squared equals 10 squared. Transpose 10 squared to the left side of the equation or add both sides of the equation by negative 10 squared. So we have now x squared minus 10 squared equals 0. Applying the difference of two squares, so we have the quantity x plus 10 times the quantity x minus 10 equals 0. Apply the zero product property, so we have x equals negative 10 and 10. Now let us check if negative 10 and 10 can be a solution in the given problem by plugging in the value of x in the problem. So let's have negative 10. The square of negative 10 is 100, so definitely the argument is positive. Also, 10 square is 100, so again, it is positive. So let's continue with the checking. When x equals 10, we have log 10 square equals 2. Therefore, 2 is equal to 2. Now, when x equals negative 10, we have logarithm of the square of negative 10 equals 2. The square of negative 10 is 100. Now, we have log 10 square equals 2. Simplifying, we have 2 equals 2. Hence, the solution are negative 10 and 10. Example number 6. The square of log x plus 2 log x minus 3 equals 0. Solution. We let a equals log x. Now this problem will turn into a squared plus 2a minus 3 equals 0. Factor. We have now the quantity a plus 3 times the quantity a minus 1 equals 0. Apply the zero product property. Therefore, a is equal to negative 3 and 1. Restore a. So we have log x equals negative 3 or log x equals 1. Transform log x equals negative 3 to exponential form. So we have now x equals 10 raised to negative 3 or x equals 1 over 1000. Now let us transform log x equals 1 to exponential form. Therefore, we have x equals 10 raised to 1, which is equal to 10. Now let us check. When x equals negative 3, therefore, we have the square of log 10 raised to negative 3 plus 2 log 10 raised to negative 3 minus 3 equals 0. Simplify. We have now the square of negative 3 log 10 minus 6 log 10 minus 3 equals 0. Again, we have the square of negative 3 minus 6 minus 3 equals 0. Therefore, 0 is equal to 0. Now when x equals 1, we have the square of log 1 plus 2 log 1 minus 3 equals 0. So we have 1 plus 2 minus 3 equals 0. Then we have 0 equals 0. Hence, the solutions are 1 over 1000 or 10 raised to negative 3 and 10. Properties of logarithmic inequalities. Property number 1. If b is greater than 0 or less than 1, then x sub 1 is less than x sub 2 if and only if log x sub 1 base b is greater than the logarithm of x sub 2 base b. Property number 2. If b is greater than 1, then x sub 1 is less than x sub 2 if and only if logarithm of x sub 1 base b is less than the logarithm of x sub 2 base b. Example number 1. The logarithm of the quantity 2x minus 1 base 2 is greater than the logarithm of the quantity x plus 2 base 2. Solution. We have 2x minus 1 greater than x plus 2 by applying property number 2. Simplifying, we have x is greater than 3. Now let us check if the logarithms are defined by checking if the arguments are greater than 0. So we have 2x minus 1 is greater than 0. Simplifying, we have 2x greater than 1. Therefore, x is greater than 1/2. Also, x plus 2 must be greater than 0. X is greater than negative 2. Now ensure that the inequality is defined by taking their intersection. So take note, in the arguments, we have x greater than 1/2, x is greater than negative 2, and the answer is x is greater than 3. Therefore, we can say that the solution is x greater than 3. Example number 2. The logarithm of x base 0.2 is greater than negative 2. This time, the base is greater than 0 but less than 1. Solution. Rewrite the right side of the inequality to logarithm with base 0.2. So we have logarithm of x base 0.2 is greater than negative 2, the logarithm of 0.2 base 0.2. So once again, let us rewrite the right side of the inequality. Then let us apply property number 1. So since the base is greater than 0 but less than 1. So we have now x is less than 0.2 raised to negative 2. Observe that the inequality is greater than here, then this one is less than. Because once again, the base is greater than 0 but less than 1. Therefore, x is less than 25. Now let us check if the logarithm is defined. The logarithm is defined when x is greater than 0. Now let us ensure that the inequality is defined by taking their intersection. So based on the argument that x is greater than 0 and the answer is x is less than 25, therefore we can say that the solution is x is greater than 0 but less than 25. Example number 3. The logarithm of x is greater than negative 2 but less than 2. Solution. Rewrite inequality to logarithm with base 10. So we have now log x is greater than the logarithm of 10 raised to negative 2 but less than the logarithm of 10 raised to 2. Split into two simple inequalities and apply property number 2 since the base is greater than 1. So let's take this inequality. So we have log 10 raised to negative 2 is less than logarithm of x. Let's continue. So we have now 10 raised to negative 2 is less than x. Or we have 1 over 100 is less than x. Also, let us take this part of the inequality. That is, the logarithm of x is less than logarithm of 10 raised to 2. Simplifying, we have x is less than 10 squared, or x is less than 100. Now check if the logarithms are defined. That is when x is greater than 0. Ensure that the inequality is defined by taking their intersection. Take note, based on the argument, x must be greater than 0. In the result, we have x must be greater than 1 over 100, but less than 100. Therefore, the solution is when x is greater than 1 over 100, but less than 100. Example number 4. ln x is greater than 1. Solution. Rewrite the natural logarithm in base e. So we have log x base e is greater than log a base e. Take note e is greater than 1. Therefore, we will apply property number 2. Therefore, we have x is greater than e. Now let us check if the logarithm is defined. That is when x is greater than 0. Now let us ensure that the inequality is defined by taking their intersection. Take note that x must be greater than 0 and also x is greater than e. Therefore, we can say that the solution is when x is greater than e. Example number 5. The logarithm of the quantity 4x minus 1 base 1 half is less than the logarithm of the quantity 1 minus 2x base 1 half. Solution. Apply property number 2 since the base is greater than 0 but less than 1. So therefore, we have 4x minus 1 is greater than 1 minus 2x. Observe the inequality sign in the problem. And when we compare the arguments, so they interchanged. Now simplifying, we have 6x is greater than 2. Then x is greater than 1/3. Let us check if the logarithms are defined. We have 4x minus 1 should be greater than 0. Simplifying, we have 4x is greater than 1 and x must be greater than 1/4. Now let us take 1 minus 2x must be greater than 0. Simplifying, we have 1 is greater than 2x. Therefore, x is less than 1 half. Now ensure that the inequality is defined by taking their intersection. So take note that we have x must be less than 1 half. Here we have x must be greater than 1/4. And when we solve the inequality, we have x must be greater than 1/3. Therefore, the solution is when x is greater than 1/3 but less than 1 half. Things to remember in solving logarithmic inequalities. Number 1. Ensure if the logarithm is defined by securing that the arguments must be greater than 0. And number 2, we have checked if the inequality is defined. That is by taking the intersections. For reference or exercises in solving logarithmic equations and inequalities, you may visit the following sites: Khan Academy, mathisfun.com, Paul's Online Notes, study.com, and purplemath.com. For your task in this session, you will be asked to solve for x that will satisfy the given equation or inequality. Number 1, the logarithm of 216 base 6 equals 3x. Number 2, the logarithm of the quantity 3 minus x base 9 equals the logarithm of the quantity 5x minus 15 base 9. Number 3, the logarithm of 5x base x equals 2. Thank you for taking time watching this video. I hope somehow this session helps you. So once again, thank you.